Welcome to Mrs. Carl's Chemistry Crash Course. Today we're going to be talking about Hess's Law. So Hess's Law states that the change in enthalpy for a stepwise process is the sum of all the enthalpy changes of the steps. So remember, the change in enthalpy for a reaction is always associated with a particular reaction. If you change the reaction, the steps in some way, then the change in enthalpy also changes, or delta H as we know it, changes in specific ways. So from the other day, remember that if a chemical equation is multiplied by a factor, then the delta H of reaction is also multiplied by the same factor. Also, if a chemical equation is reversed, then the delta H, or change in enthalpy, changes its sign. So that's going to help us go through Hess's law, because we want to make sure that all the intermediate steps add up to the final reaction that we're talking about and that we're describing. So that's important. All of the intermediate steps have to add up to the final reaction that we're looking at. Let's all know that Hess's law follows from the enthalpy of reaction being a state function. So recall what a state function is. That doesn't matter how we get there. We're looking at the initial and the final states of a reaction. So let's look at this reaction. So we have an example just with A and B to make it a little easier. So we're going to add up the individual steps. So this is a two-step process. We're going to add that up, and we're going to get an equation. So notice that in the first reaction here, C is produced. So C is a product. In the next reaction, C is a reactant. So if we produce it in one reaction, and then we use it in the next reaction, it just kind of gets used up. So that gets crossed out. In our overall reaction, we add this up. A plus 2B, those are our reactants. We're not going to include C because we produced it in one, we used it in the other. Yields 2D, our product. So in this situation, you're going to add delta H1 and delta H2 of each reaction to get the overall change in enthalpy. So that's what we're looking at, is just the overall change in enthalpy. So why do we do all this? Why do we add up steps, so on and so forth? This makes it possible to determine some heats of reaction, enthalpy changes for a reaction, without directly measuring it in a laboratory, because some overall reactions are very difficult to measure. But if we can find steps that lead up to our overall reaction, and we can add them up, then we can find the overall delta H of the reaction that we're looking at. So here's a reaction that is between solid carbon and water, and this is an industrial way, an industrial method for generating hydrogen gas. So we want to know, what's the delta H of reaction for this one? So what's the change in enthalpy? Well, there are three intermediate steps that can lead us to that. So we're going to take the process we learned the other day and a little bit in this video, and see if we can't solve for the change in enthalpy for this reaction. So let's look at our intermediate steps, and our goal is to take these steps, add them up, and get an overall change in enthalpy. So all of these steps should add up to carbon solid plus water gas produces carbon monoxide gas and hydrogen gas. So let's look at our first reaction here. We have carbon solid as a reactant. In our final equation, we have carbon solid as a reactant. So we're going to keep that reaction just as it is. We don't have to reverse it, we don't have to double it or have it or change it in any way. So we're going to keep that one. Okay, let's look at our second reaction. We have carbon monoxide plus oxygen gas. Now, in the equation we want, carbon monoxide is a product. So we're going to have to reverse this reaction. If we reverse the reaction, we need to change the sign from negative to positive. There's another thing here. In our final reaction, we only have 1 mole of carbon monoxide. In this one, there are 2. So not only do we have to reverse it, we have to take this whole reaction, including the delta H, and cut it in half. Okay, so I'm going to rewrite this one because we won't be able to use this step as it is written. Okay, here's our second reaction rewritten. It has been reversed, so now we have our carbon monoxide in the products, just like we do up here. We cut it, so we reversed it, so we changed the sign, so now it's positive. We had to cut the whole thing in half because we only had 1 carbon monoxide in the products in our overall reaction. So notice, we did half oxygen there, and we cut our delta H in half to 283 kilojoules instead of 566 kilojoules. Okay, let's analyze the third reaction. So we have hydrogen gas as a reactant here in this one, but it's a product in our overall reaction, so again we're going to have to reverse this. And if you notice, there's only 1 hydrogen gas in what we want. There are 2 here, so we're going to have to reverse and cut it in half just like we did to the last equation. Well, I didn't leave myself much room, but hopefully you can see the final equation for equation 3. So let's go through and see what are intermediates, what can we cross, what can we cancel out, and then we're going to add up our delta H's just to make sure that we have this correct. So in the first reaction, we produce carbon dioxide. In the second reaction, we use it. So we're just going to kind of cross cancel those because it's produced in one, we use it in the other. And we could do this when we write out the final equation also, but sometimes it's easier to look step by step. So we could write everything and then cancel what's the same on either side of the yields arrow. So we need the carbon monoxide, we need the water. The oxygen gas we don't need. Notice how there's a full oxygen gas there in a product, and in the reactants on the next 2 we have half. So half plus half is going to give us a whole, so that oxygen gas is going to get canceled out, and I believe that takes care of our overall reaction. So let's add up all of the compounds and elements, and then we'll add up our delta H's. So when we add everything up, we get carbon solid reacts with water gas to produce carbon monoxide gas and hydrogen gas. Our delta H of reaction is a positive 131.3 kilojoules. Since it's positive, take a moment and decide, is it an endothermic or exothermic reaction? And if you said it was an endothermic reaction, you are correct. So let's give you some practice. So your turn. Let's take this reaction and find the enthalpy change for the overall reaction. Give you a moment to pause the video, work it out, and come back for an answer. Okay, so here are all your steps that have been halved and reversed and whatever needed to happen with them. I did this one a little bit differently. At the bottom you can see I just wrote down everything. So I brought everything from the top down. So our nitrogen dioxide I brought over, nitrogen gas, oxygen gas, dinitrogen oxide, everything I brought down. So now we can see what cancels. If it's the same on both sides of the equation, we can cancel it out to make sure it matches our final equation. So I have 1 nitrogen gas in the reactant side, and I have 1 nitrogen gas in the product side. So that can get canceled out. I have one oxygen gas in the reactant side, and I have 2 halves of oxygen gas, so that's a whole. In the product side, and I should have 3 nitrogen monoxides right there. Okay, so let's write our overall equation and add up our delta H's. Right, there's your overall equation and your delta H of reaction. Another positive one, so another endothermic process. Hopefully you learned something, and take care.